So this is our third webinar in our series of cybersecurity risk assessments and security level verification, and we will be focusing specifically on the security level verification in this webinar. Before we jump into the webinars, I always like to introduce myself and just give a brief background. My name is Patrick O'Brien, and I'm a safety and cybersecurity engineer with Exida. My background is in chemical engineering, but I've worked over the last few years in various roles at Exida, from cybersecurity consulting to process safety consulting and many other areas as well. And I was a co-author on our new cybersecurity book, Implementing IACS 62443, a pragmatic approach to cybersecurity. My email is there in the bottom, so please, if you have any questions on the topics of this webinar or any other cybersecurity or safety related questions, please feel free to reach out to me. Exida, just again, a real quick background, is a customer-focused company, and so they focus on helping our customers achieve safe, reliable, and secure solutions. And we do that in three main ways. The first of which is our powerful lifecycle tools. So specifically in this presentation, we'll look at Exida Cyber and how we can use that as part of our work process for cyber risk assessments and security level verification. The next is our certification and assessment body. And so that will certify devices and systems as well as personnel to the applicable functional safety or cybersecurity standards. And then lastly, we have our lifecycle services, so working with the end users to deploy solutions for cybersecurity, functional safety, and alarm management. Exida is a global company, and I am speaking today from our office outside of Philadelphia, our US headquarters, but each of the Exida icons represents a different location on the map. So hopefully you see a location near you, but if you don't, we do have the ability to support projects really anywhere in the globe. We also work across many different industries, from oil and gas, both upstream and downstream, chemical facilities, a number of alarm management projects, the automotive industry, both in Europe as well as in the United States, as well as power, additional alarm projects in Asia Pacific, and liquid natural gas. So really, when it comes to functional safety or cybersecurity, regardless of the industry, we do have the expertise to work on those projects. When we look specifically at cybersecurity, there are a number of ways that Exida can help. For our consulting services, we offer the ability to go in and do these cyber risk assessments and security level verifications, as well as many other lifecycle tasks. We offer certification to ISA Secure and different parts of the IACS 62443 standard. We also offer a number of training courses that cover the cybersecurity lifecycle. And then we have our Exida Cyber tool that we'll see some screenshots of, as well as a lot of different reference material. Our presentation today will focus on three main parts. The first will be our integrated lifecycle approach, so understanding how functional safety and cybersecurity can work together. Next, we will go through and look at the method for security level verification and work through a detailed example. And finally, we'll look at the security level verification results and understand how the outputs of SL verification can be useful in making decisions regarding risk management. So before we review the lifecycle approach to risk management, I want to jump to our next poll question and just get an idea of how many people have been to previous webinars in this series. So please take a second and just answer the poll question, and we'll just use that to understand how much to go through in terms of review. So please just take a second to fill that out now, and we'll be happy to kind of tailor the rest of the presentation accordingly. Okay, so we'll give it another 10 seconds and see where the responses come out. Okay, so we've got about maybe 60% who's been to some combination of the first two webinars, and about 40% who haven't. So we'll do a kind of a brief introduction, but there is a lot to cover for security level verification, so we won't spend a ton of time on review. When we talk about the integrated life cycle, we're really looking at ways where the life cycle tasks for functional safety, alarm management, and cybersecurity can work together. And when it comes to managing risk on a facility level, it's really important to be aware of both the safety and the cybersecurity risks and understand how that is going to impact the overall reliability and safety of the system. And so what we can do is we can take the relevant industry standards looking at the 61511 life cycle and the 62443 life cycle for security and see where those activities overlap and where we can have added efficiencies, added benefits from working together. And so one example that we saw was the need for process hazard information to be available when actually going in and doing the cybersecurity risk assessments. So this represents one area where there's important overlap between the cybersecurity tasks and the functional safety tasks. And so understanding that can allow us to be more efficient when doing the lifecycle activities. Two things that we'll briefly touch on today are also the foundational requirements for the life cycles. So understanding that both the alarm management, functional safety, and cybersecurity lifecycle, all of those tasks to be successful really need to be carried out by personnel who are well trained and are able to show the correct level of professional competency. And so making sure that you have the training procedures and the competency evaluation procedures in place to verify this can be very important in making sure that the tasks are done correctly. Additionally, having certified devices, elements, and systems that can meet your systematic capabilities, both for functional safety and cybersecurity, is also very important. And so that really lays the foundation for being able to go in and have successful completion of these lifecycle tasks. When we focus in specifically on cybersecurity, we're looking at the IACS 62443 lifecycle. And this lifecycle has a number of parts that apply to the end user, the asset owner, to integrators, as well as to the original equipment manufacturers. So it's important to be able to go through it and look at what specific parts of the standard apply to you and understand how they work together in the overall scheme of addressing cybersecurity. So in this webinar, we'll be specifically looking at the portions that apply to the end user and actually putting together that final system and addressing cybersecurity. And so when we look at this portion of the standard, we see the overall cybersecurity lifecycle, which covers the assessment phase, so understanding what the cybersecurity risks are through the implementation phase of actually designing our system with countermeasures, and then finally the operations and maintenance phase, so making sure that we're able to maintain our IACS in a secure manner throughout the life cycle of the facility. One example that we've worked with in our other webinars is our Sadara Petrochemical facility. And basically, we won't go in depth on the incident because we've covered that on the first two webinars, but the key takeaway are that attackers were attempting to cause a deadly explosion. And so this was a cybersecurity attack that was really one step away from having very serious safety consequences. But the attack didn't end up being successful because the safety system was redundant and only one of the controllers was compromised. So the other was able to bring the system to the safe state and avoid the consequence from occurring. When we look at really what leads to a successful attack and what kind of goes from making an attack be just some threat that's potentially able to access the system to go all the way through and become a successful attack, there are three factors that we want to look at: the threats, the vulnerabilities, and the target attractiveness. And as we go through and work with our security level verification worksheet, we'll see how each of these really does impact the overall successfulness of the attack and can help us calculate really what risk reduction is necessary for cybersecurity. And the last thing we want to touch on is just that although we do focus a lot of time discussing the intentional cybersecurity attacks, such as the Sadara Petrochemical facility, the majority of cybersecurity incidents are actually unintentional, 80%. And these are things such as really just general malware that might accidentally get installed onto the control system, or improper configuration for network commitment, and these things can lead to unexpected downtime and cause some annoyances when dealing with cybersecurity. So in our first part of the series, we looked at the high-level risk assessment, so going through and identifying what the the overall scope of cybersecurity, establishing our zone and conduit diagram. Our next discussion was the detailed risk assessment, so taking the outcomes of our high-level risk assessment and really going down and evaluating the threat vectors at a granular level. And then today we will finish up this series by looking at the security level verification and actually validating our design to make sure that we achieve the security necessary. So before we go and look at the security level verification, I just want to get a quick idea of how familiar the audience is with security level verification. Is this something where people have heard about it in depth, or where they're maybe not as familiar with it? And that can just be helpful in terms of understanding what level of detail to go. So please take another 10-20 seconds and answer, and then we'll kind of review and go from there. Okay, we'll give it 5 more seconds. Okay. So it looks like we've got maybe about half somewhat familiar to very familiar, and then another half not particularly familiar. And that's great. We're happy to go through it and really explain that, and hopefully we'll be able to go through and give a little bit more of an in-depth analysis for those who aren't as familiar. When we look at SL verification, we want to think about in terms of what are the necessary inputs. So what information are we getting from our high-level and detailed risk assessments that are needed? What are the steps that we have to go through? So understanding that we'll start with getting our cybersecurity events and countermeasures. Then we'll go through, we'll look at our target attractiveness and understand how kill chain relevance and conditional modifiers can affect the likelihood of successful attack. And then we'll go through and really determine countermeasure effectiveness and how it applies. And lastly, we'll go through and review, has our target likelihood been met, and did we achieve really the necessary systematic capability? And then that will give us, our verified design for our future lifecycle tasks. To briefly review, we'll be going through this exercise using an example styrene facility. And so this is a plant that converts 1,3-butadiene through 2 reactions to styrene. It's the 60,000 pounds per hour of high purity styrene is a pretty normal amount of styrene that is produced. So we can think of this as really just some medium sized chemical facility. If you look at a simplified block flow diagram, we can see that we've got an extractive distillation process to get high purity 1,3-butadiene. That is fed to a vinyl cyclohexene reactor, so that is our intermediate that's produced. There are a number of purification steps and then additional mixing to add in oxygen before the second reactor. And then from the second reactor, it is the styrene that is separated and then captured with high purity. So when we talk about the inputs for SL verification, we'll start with really having that process hazard information. And so this was key for our risk assessments as well as for the security level verification. And so when we look at specifically that styrene reactor in our block flow diagram, and we think about the potential unintended reactions, the effects of high pressure and high temperature, we can see that a large safety case that we really will have to consider is a runaway exotherm that has the potential to lead to vessel rupture with a single fatality. And so when we take this scenario and we review our risk matrix and our tolerable risk frequency, we can see that it's going to correlate to security level 3 for the severity. And so we have to consider that, in this case, if the IO is manipulated, there's the potential for that single on-site fatality. And so at security level 3, we can go and look at our tolerable frequency to determine how much risk reduction is necessary to bring this within our organization's risk criteria. And so based off of our example risk criteria, the tolerable frequency for a security level 3 type event is 1 in 10,000 years. So when we go through and do our cybersecurity level verification, we'll have to make sure that we are reducing the risk at least to that level. When we look at our zone and conduit diagram, we're going to be focusing in again on our BPCS zone, and we saw that this has a security level target of 3. So that is the security level that we will have to verify to. Next, we'll look at really the outcomes of our detailed risk assessment, which will directly feed into our security level verification. So the first thing that we have to look at are the threats. So we've gone through and identified the different threats that can be used to gain access to the system. We have identified the countermeasures that are in place. So understanding what different protection measures are there that could try to stop these attacks from occurring. And then finally, we've got a last column where we can identify whether or not security level verification is going to be needed. And this is where we can mark information that is going to be needed then to transfer to our security level verification. So that takes us to really our first step in our security level verification, and that is transferring existing cybersecurity countermeasures and events to the security level verification. And really the importance here is making sure that all of the information captured in the detailed risk assessment is available to the personnel going through and then performing the security level verification. And so if the analysis is performed using the exida tool, there's the ability using these buttons to really automatically transfer all of the relevant information from our Cyber PHA module to our Cyber SL module. And so it will ask you, a couple questions to make sure that you want to merge, but then you're able to pull over all of the relevant cyber threats as well as countermeasures for our specific cyber event scenarios. And so this allows us to make sure that we have all of the threat information and all of the countermeasure information that's a necessary input readily available for our security level verification. The next step is then to really go in and look at our target attractiveness and kill chain relevance. When we talk about target attractiveness, really it's some multiplier that is greater than or equal to 1, which considers how likely a facility is to be targeted. So a couple of things that might be considered when addressing target attractiveness would be the relevant industry, the size of the facility, the company who's operating the facility, relevant, political, personal, economic motives, anything that could really drive someone to target that facility specifically. And so one way to do that is to have an example categories of target attractiveness. And so an organization can define really different levels and sizes of plants and then address which of those facilities are most likely to be targeted. So if we start with a small impact target, that really is just a small, there are many different types of plants that can provide the same, commodity, then that's something where it may be a less attractive target. If we bump up to regional impact, it's still a somewhat smaller plant, but there may not be as many different sources in a specific region, so it could have an effect in that region. Next, we would bump up to something that is, say, a single source. So this might be a more critical company asset. It's some sort of specialty chemical that really there's only one type of producer of that and could have a meaningful impact for a successful attack. And then the highest level of target attractiveness might be something such as a critical infrastructure target. So some sort of national infrastructure that could have extreme safety or environmental consequences for the public if there was a successful attack. So based off of these categories, where do people think that our styrene facility might fall? So I put the options up, so please just take a quick second to answer in the poll, and we'll see where people feel the facility will fall. And this is just a guess, so no wrong answer, so please feel free to just put where you would place it, and we can kind of look and see what people are thinking. Okay, we'll give it another 10 or so seconds and see where most people are falling. So it looks like we've got a little bit over half saying a single source or large impact target, some saying critical infrastructure, and some saying regional impact. So when I look at this, I would guess, I would personally put it at say, a regional impact. I think you could definitely make an argument for single source, and that would kind of depend on what other producers of styrene were in the area. So something between maybe that regional impact to single source is what I would expect. I would say that it probably isn't quite up to critical infrastructure, just because the overall impact of that facility being shut down may not have as severe of a consequence. But understanding that all of these different factors can play a role in really identifying what the target attractiveness is for a system is important, and really all of that does play a role in how likely it is for one of these engineered, more targeted attacks. When we look at understanding the cybersecurity kill chain, this is a model that was developed by Lockheed Martin, and really the idea is to outline all of the steps necessary to go through and have a successful cyber attack. And so the idea is that if you break this chain at any point, you could prevent the ultimate consequence. So this can be helpful when considering really what countermeasures could be installed on the system, and also just understanding what level of sophistication is needed for the attack to be successful. So the chain starts out with reconnaissance, so just something as simple as really harvesting potential email addresses, getting information about the type of plant that's being run. For more engineered attacks, actually getting the ability to access piping and instrumentation diagrams can be very important for reconnaissance, for really identifying the most important parts of the facility to target. And it goes through, and there are a number of different steps. So you could see from then weaponization, so taking what you know about the process and figuring out an exploit in a way to then deliver it to the system, actually being able to get the malicious code installed somewhere on the network, whether it's through email, the web, or a USB stick, and then actually taking that vulnerability and being able to execute the code on the system, making sure that you're able to install the malware on the correct asset. And then finally getting command and control for really being able to have that remote control of the targeted asset, and ending up achieving your final actions on objectives. And so if we think about maybe having a really robust cyber hygiene policy, not having any sort of footprint where our network can be discovered on the internet, doing all of these things to really reduce the likelihood that they're able to get these email addresses or understand how the system is set up, we have the potential to stop an attack there. Or if we think about maybe delivery, so even though if they are able to find an export and have some malware targeted for our system, if they're never able to install it, if all of our ports are blocked, if we really are good about making sure that our network is air-gapped and that it is protected from really unwanted communication, then maybe we're able to stop it at the delivery phase. If we think about installation, maybe they are able to get the malware installed on our engineering workstation, but before anything is downloaded to our controller, we review the code, we make sure that the detailed signatures are all there, and we do an analysis to make sure that everything is ready to move forward before anything is connected to our logic controllers. And so at each of these steps, there is the potential for us to stop the attack from occurring. And so those are places to really identify different countermeasures that could be effective. When we look at really understanding how kill chain relevance affects our likelihood of a successful attack, there are maybe two examples that we can look at of maybe attacks that would be less likely to be successful. So the first thing to look at is what level of reconnaissance is needed to have that successful attack. So are they able to quickly find entry points into the system? How difficult is it to determine what could be a high consequence severity for that system? And if that is something that's very difficult and is going to require analysis of detailed piping and instrumentation diagrams, it's going to require all this information to really target the system, then you might be able to take some credit that isn't going to be readily available to all attackers. Another question would be to look at, well, how many different zones really need to be compromised in order to have that undesired consequence? And so if we know that we need to compromise not only our basic process control system, but also our safety instrumented system, and those zones are kept, completely isolated, they are properly segmented, and it really would be two separate attacks to gain access to both of those, then there's some likelihood that the attack won't be able to do both successfully. And so that is one way where we can take credit for kill chain relevance. When we look at conditional modifiers, these really are similar to the conditional modifiers that we would see in the layer of protection analysis. So things such as occupancy. So even though they are able to go through and cause that vessel rupture, if our operators and maintenance personnel are only in the area for around 25% of the day, we could take some credit that there's a likelihood that they may not be there. Essentially, it's really any probability that a given hazard scenario may or may not lead to a consequence. So if we think about our vessel rupture, if the vessel did rupture and there was a release of the flammable vapor, there's going to be some likelihood that there's no spark present. So maybe we just have a release event. And then there's going to be some likelihood that there is a spark, which could lead to an explosion. So at each of these steps, we can take credit that the worst case scenario isn't always going to be 100% likely to happen. There is some likelihood that different scenarios could take place. Once we've gone through and addressed all of the modifiers that can affect the likelihood of the successful attack, we're able to actually go in and look at the countermeasures to determine the overall effectiveness and then which specific scenarios they would be applicable to. So when we talk about cybersecurity countermeasures, we're specifically looking at what could be in place to stop an attack. So either reduce the likelihood that the attacker can gain entry to the system, reduce the likelihood that the attack goes unnoticed, or reduce the consequence of the attack. So if we think about these three categories, I'm going to pull a question that we had from our detailed risk assessment webinar. But it's basically which of these different options, the pressure relief valve, the hardwired interlock, or the firewall, what ones could potentially stop an attack from occurring, reduce the likelihood that the attack goes unnoticed, or reduce the likelihood, the overall consequence of the attack. So please just take a second once the poll pops up to determine which of those would be countermeasures. So we'll give that another 20 or so seconds, and then we'll kind of review the answers and see what people are thinking. Okay, 5 more seconds. Okay. So we've got a good split. So we've got some people thinking the pressure relief valve, some thinking the hardwired interlocks, about a third saying the properly configured firewall, and a little less than half saying all of the above. And I do apologize, this is kind of a tricky question, but the correct answer is all of the above. And so the properly configured firewall would be an example of a countermeasure that might reduce the likelihood of the attacker gaining entry into the system. And then the pressure relief valve and the hardwired interlock, both of those are devices that wouldn't be susceptible to cybersecurity attacks. There's no way that the attacker could try to hack the pressure relief valve and stop it from functioning to relieve pressure in the system. So those would both be examples of countermeasures that could reduce the consequence of the attack and wouldn't be susceptible to be disarmed by that attacker. So those would be countermeasures as well. So kind of all of those would be ways to actually try to reduce the overall consequence or likelihood of that attack. When we're really determining countermeasure effectiveness, there are 3 questions that we want to look at. The first is the countermeasure independent from other listed countermeasures? And that really is necessary in order to have that countermeasure listed for it to have any effectiveness. We must really be able to show that it is going to be effective from the other countermeasures listed. Next, we'll ask, well, is the countermeasure something that could actively stop an attack, or is it passive? Does an operator need to review something in order to realize that an attack may be going on and then take a set action? And then lastly, is the countermeasure applicable to a given threat vector? So will this countermeasure, we know that it's independent, we know that it has some level of effectiveness, but does it apply to a given situation? And those are kind of the three things that we will look at. So there have, kind of as I've gone through and given these talks, there have been a couple of questions on what does it really mean for a countermeasure to be independent? Because if we think about it, a well-designed attack, a knowledgeable attacker, may be able to go through and overcome many different countermeasures. So if one attacker has the skill to go through and disable multiple countermeasures, how can you say that they are then independent? And it's a good question. It's a good point to bring up and consider. But the key when we think about independence in cybersecurity countermeasures is that one specific attack type will not be able to get through more than one layer of defense at a time. So if we think about a threat vector where the attacker has the administrative access, so he has the password and logon for the administrative account, that may give them the ability to modify the engineering workstation, may give them the ability to access through the firewall, and then actually configure the BPCS. So in that scenario, based off of the configuration of the firewall and the engineering workstation, those would not be two independent countermeasures because that one attack vector, that one method is able to bypass both of them. But if we had separate accounts where there were accounts to access the firewall and then set accounts that are really only for accessing the engineering workstation, then because two different accounts are needed, there's not one way of overcoming both measures, then they would be independent. Also, if we had, a managed switch in place that really did maintain the independence of our safety system and our BPCS, then we could say that that might be an independent countermeasure. But if at our operator workstation, there's the ability for operators to actually bypass the safety system, maybe for testing purposes or anything like that, well, then we would know that we couldn't really take credit for our BPCS and safety system being separate, because if the attackers do gain access to the engineering workstation or the operator workstation, they can then bypass the safety system and make sure that it won't work to try to stop the attack. So it's really important to think about, is there one attack that an attacker could use to go through multiple levels of the countermeasures, and really making sure that each countermeasure is independent and provides additional protection. When we consider whether or not a countermeasure is active or passive, it comes down to how much risk reduction should be claimed for that countermeasure. So for active countermeasures, these are anything that will actively prevent a successful attack from occurring without operator intervention. So this could be something such as a well-managed firewall, or maybe hard-coded endpoints in the controller code. And so in either case, without the operator taking any action, there's something in the system that can stop the attack from occurring and propagating to that next level of the kill chain to going on and being successful. And so for that, we could assume maybe a conservative probability of countermeasure failure of 0.1. For passive countermeasures, these are things that have the ability to prevent an attack if the operator kind of reviews the information and takes a defined action in time to prevent the ultimate consequence. So this might be something such as reviewing firewall logs to see if there's unusual access, or reviewing the code of the controllers periodically and making sure that nothing has been changed since the last scheduled download. And so because many of these engineered attacks aren't immediate, it's not as soon as malware is on the system that they're able to then gain access to the BPCS and the safety system, there's typically is some time and place where some code, some malware is present on the system, but not enough has been achieved to then move to that overall ends-on objectives. So there is time available for these periodic reviews, say if they were done on a quarterly basis, to have a chance of really identifying different cybersecurity intrusions and then taking steps to mitigate that risk. So we might give it a somewhat lower probability of countermeasure failure of maybe 0.2 as opposed to 0.1 for active countermeasures. The last step is then to go through and figure out whether or not a specific countermeasure is going to be applicable to a threat vector. So if we think about some cybersecurity threats for social engineering, so different ways that the attack could be compromised via the people, we could look at three different threat vectors. So the first would be some sort of stolen credentials through a spear phishing campaign. The second could be passwords are left in the open, so anyone with in-person access is able to go on and take advantage of the control system. And then finally, we might look at our third-party contractors and see whether or not there's the potential for them to bring malware into the system. So if we think about these entry points that could lead to that single point IO attack, the manipulation of the basic process control system, we could then review the different countermeasures and see, well, what countermeasures are going to apply to which situations. Something like validating the code with detailed signatures before downloading it to the controller, regardless of the method used to gain access to the system, whether it's through a phishing campaign or generic credentials, if that review is carried out, if the code is validated before downloading, then that is something that will identify a problem and has the ability to stop the attack before it propagates. So that would apply to all three scenarios. If we look at something like making sure that the passwords, if they are written down, are kept in a locked box or a secure location, that could be useful in reducing the likelihood that anyone with in-person access can just log on to the system. So we might say that that is going to be effective for our generic credentials scenario, but that would not really reduce the risk of our phishing campaign or of third-party contractors potentially being an entry point in the system. So it would not apply in those cases. If we think about cybersecurity training on cyber hygiene for our personnel, well then, yes, that could potentially reduce the likelihood that the information is gained via a phishing campaign, as well as reduce the likelihood that passwords are in the open. So that may be something that applies to both of these cases, but it would not apply to the third-party access because they aren't going through this training, and so you can't be certain of the different practices that they are following. And so the last two then things looking at making sure that we're presenting any unnecessary control reports being available or really doing that job cyber assessment to make sure that when third-party personnel are coming on to do tasks, that they have specific things that they're allowed to touch. They know exactly what the scope of the interaction with the IACS can be. That then has the ability to limit the likelihood of a successful attack in that scenario. So by going through and figuring out, making sure that the countermeasures listed are independent from other countermeasures, making sure that we've accurately identified how effective they might be, and then going through and figuring out specifically to what threat vectors do they apply, that allows us to do a somewhat robust method of really having a semi-quantitative approach of addressing the current level of risk. And so this does vary from potentially quantitative methods used for functional safety because there isn't that breadth of data, there isn't enough knowledge to really be able to say exactly what the failure rate of that cyber countermeasure might be. When doing a layer of protection analysis, you can look at your pressure relief valve and you can point to a book that says really exactly what that failure rate might be. And so that allows you to be very quantitative in the method. The level of information that data capture isn't quite there yet for cybersecurity concerns, but it is likely something that's going to be tracked more in upcoming years. But this approach allows us to have an effective semi-quantitative way of really addressing how much risk is currently in the system. And so after going through and looking at all of these different areas, we've been able to show what the current level of cybersecurity risk is. So the questions are, have we met our target likelihood and have we achieved the necessary systematic capability? When we look at evaluating the remaining risk, it's really a comparison of what the current likelihood of a successful attack is to what our target or the necessary likelihood we have to reduce for our risk criteria. And so in a case where we aren't yet meeting the likelihood of successful attack, and that is calculated by looking for each specific threat vector, how likely that is to go through and be successful. If we aren't meeting that target, we can actually look and see which of these threat vectors are giving us the highest contribution to that overall attack. And we could see that maybe we have enough countermeasures in place to reduce the likelihood of our third-party attack, but for our stolen credentials and generic password, additional countermeasures are needed. So that could target really where we need to take additional risk reduction activities. When it comes to identifying whether or not the systematic capability has been met for our system, there are a number of different approaches that could be used. The IEC 62443 3-3 standard provides 7 foundational requirements. And for each of these foundational requirements, there are supplemental requirements and requirement enhancements. And so if a system is shown to meet all of the security requirements and the requirement enhancements for a foundational requirement, then you can go through and justify that that system was able to meet that security level for that area. So if we look just at our foundational requirement 1, which is identification and authentication control, for a security level 1, all that's required is that there is human user identification and authentication. For security level 2, there's an additional requirement that there has to be unique identification and authentication. If we look at security level 3, then there's multi-factor authentication introduced for untrusted networks, and then for security level 4, there's multi-factor authentication for all networks. And so this is one method of going through and doing security level verification, and that would be an example of a qualitative approach. One way to really combine this to make sure that we're addressing the systematic capability as well as meeting our overall risk reduction needs is to do some combination of this systematic capability analysis with the semi-quantitative approach that we looked at from our SL worksheet. And so in this case, what we might do is determine the security level using the risk-based targets, as we went through and did in this series. We would make sure that both the physical and personnel security are consistent with our security level target. So this would mean for something like a security level 3 zone that we make sure that it is physically isolated, so maybe locked in a locked control room or in a locked cabinet, so providing that extra physical protection kind of commensurate to the level of risk for that zone. And then finally, we would make sure that the development of the devices and systems used in that control network really do meet the appropriate requirements of sections 4-1 and 2-4 of the 62443 standard, respectively. And so using certification is a way to show that that systematic capability for components has been met and can, in combination with the semi-quantitative approach, be used to justify that the appropriate security level has been achieved. So when we go through and do this analysis, it then allows us to kind of scope the upcoming lifecycle steps. So we can make sure that we verified our conceptual design to meet cybersecurity needs. We can prepare for then the construction and operations / maintenance phase of the lifecycle, so all of those subsequent steps after our conceptual design. We can get more detailed requirements for each countermeasure, and then we can have assumptions to actually go in and evaluate during our operations and maintenance phase. So if during our security level verification, we assume that we're only going to see a targeted malware type attack once in 10 years, just based off of the level of sophistication needed, if within our first 5 years of running the facility, we've already had 3 or more of these really targeted attacks, then we could say that our assumption of once in 10 years was not a good assumption, and we have to consider that within a higher likelihood. What it also allows us to do is actually go in and identify, the real cost of cybersecurity incidents to figure out whether or not additional countermeasures would be justified. And so for cybersecurity incidents, they could have real costs in safety on the public image of a company. If we look at our Marucci Shire example, they can have significant environmental damage. But specifically what we'll look at here are some of the business consequences. So we'll look at the damage to equipment and lost production. In our earlier webinars, we went in and calculated based on the throughput of the Styrene and the cost of Styrene per pound, really for an unexpected shutdown of 1 day. So if there are 24 hours in a year where the plant was shut down due to cybersecurity anomalies or some sort of general malware scare, that would roughly cost about $1 million. And so in addition to that, if we look at our more severe case where there's actually the vessel rupture, we can look at how costly it is then for the damaged equipment. So if we do a quick capital cost of what it takes to build the Styrene reactor, we could see that it would be roughly a little bit over $17 million with an installed labor cost of adding maybe another $5 million. In addition to really just the direct cost of the Styrene reactor, we would have to think of the additional costs as well. So what cleanup costs are there associated with replacing the reactor? What auxiliary equipment was also damaged during the rupture? So what nearby pumps, other vessels, other tanks, what else was damaged in the incident? And then how much downtime is there going to be before you can replace? How quickly can you have a new reactor fit into your system? Are you going to be down for a week, for a month? And so all of these really can go and increase the cost of a cybersecurity incident. But so for our scenario where we think about having the Styrene reactor needing to be completely replaced, we might say that conservatively that could cost maybe $50 million. So the question is, if we understand how much a cybersecurity incident might cost, how do we justify investing money for cyber risk assessments and for countermeasures? So for this one, if we think about case one, so the potential downtime, would spending $100,000 on cybersecurity countermeasures be a reasonable investment? Would that be something that would provide value? So please take a second to answer the poll, just a quick yes or no, and then we can go through and look at kind of how some of these calculations can be completed. So we'll give it another 10 or so seconds. Please, just answer the poll. Great. Okay. So far, everyone thinks that it's a good idea. And so what we can do is go through and look at really how that would work in terms of a monetary analysis. So if we assume that we are going to have a 15-year mission time for a plant at an 8% interest rate, we can go in and figure out what the expected loss saved is going to be. So for each incident, if we reduce the likelihood per year from 1 to maybe 1 in 1,000, we can go through and calculate how much of that is going to be saved. Then we can determine what the present value of that money is if we were to save that payment each year. And by doing that, we could show that throughout the life cycle of the plant, being able to reduce 24 hours of unexpected downtime a year would save us roughly $8 million. And so for that initial $100,000 to do the assessment to identify and install countermeasures, we would have a high return on investment, and we would get a yearly return on investment of around 33%. And just for reference points, for a lot of capital projects in the chemical industry, around 17% ROI is typically the say yes point, and that varies for different industries and for each company. But basically, that would go to show that from a justified spending perspective, that in this case, spending $100,000 on cybersecurity would be supported. If we think about our other case, so if we look at the potential equipment damage, if we say that the likelihood before countermeasures is 1 in 10 years, so that more targeted malware type attack, but that we are able to reduce it to our tolerable frequency of 1 in 10,000 years, would spending $1 million to do that be a good investment? And so we can go through and do the same level of calculations, assuming the 15-year mission time and 8% interest rate. And if we go through and figure out how much that might save using the same equation, we could see that preventing that vessel rupture over the life cycle may have roughly a $43 million benefit to the company. And if we go through and do our return on investment calculation with our $1 million investment, we would see that we still have a relatively high ROI of 28.3%. So if we go just off of this math, then kind of the conclusion would be that, oh, well, of course, you should always spend money on cybersecurity. But if we were to take this and go to the people in charge of the financial decision, they still may be running away from us with budget saying that they're not quite buying it. And so I'm sorry, I couldn't help but put this clip art in here because I think it often shows what happens when we go asking for money for cybersecurity or functional safety. And there, so the question is, well, how good were those two examples? Is that an accurate way of considering how much risk reduction or how beneficial the cybersecurity countermeasures would be? And there are a couple of points to look at. So the first would be, the return on investment is really heavily dependent on the existing security of the facility. So both of those examples come from the likelihood of the threat. So kind of saying that there wasn't any existing countermeasures in place and that there was nothing really to reduce that likelihood. So the question is, how confident are you in your existing countermeasures, and do you have the analysis in place to actually look at and quantify how likely these different cybersecurity events are to occur? And then the next two really come down to understanding that if there was an investment in cybersecurity, there's going to be a guaranteed upfront cost. So there is that initial investment so we looked at, say, an example of $100,000 or $1 million. So there's, regardless of what it is, there's some upfront spending that's going to go into the countermeasures, the assessments, and the loss, if those countermeasures are not present, is uncertain. There's no way of going out and saying that if this countermeasure isn't there, then this will 100% happen, and we will have this many hours of unexpected downtime. We will have this potential for equipment damage. We can do those calculations and estimate and say this is what we would predict to see. But we often run into people who believe that no one would ever target my facility, or that incident could never happen to me. So all of those kind of concerns can be why it's sometimes difficult to justify spending in cybersecurity or for functional safety, for example. But the key is, by going through and doing security level verification, you can identify really how many countermeasures are currently in place for the system, identifying how much risk reduction is achieved, and then any gaps between the tolerable risk criteria and where you're currently at. You can really look at specifically how much risk reduction is needed. You can understand really what the monetary value of that risk reduction would be, and make informed decisions regarding additional countermeasures. And so that really goes to the goals of our SL verification. We want to make sure that our design meets our cybersecurity risk, and then in areas where it doesn't, we want to look at, well, what the benefits of additional countermeasures might be, so we can make well-informed decisions on whether or not it makes sense to go ahead and add those countermeasures to the system. And then overall, making sure that we're maintaining our cybersecurity during operations and maintenance. So we went through and we looked at the integrated lifecycle approach, the SL verification method and example, and then the SL verification results. So that takes us to the end really of what we were looking at in this series. So I just want to see how engaged did you feel by this series? Do you think that it was informative or useful? So please take a second to answer the poll. Please feel free to be completely honest. I won't share the results of this one. So this is just for us to get an idea of how well we're doing in terms of talking about topics that are interesting. If you have any ideas related to cybersecurity or other concerns that you think would be good to look at in upcoming webinars, please feel free to comment them or really ask questions, anything like that. Please feel free to do so. So we'll leave the poll up for about another 20 seconds or so, just to see where people are at in terms of how helpful they found the webinars, and then we'll go and just finish up the presentation and do any questions. So thank you very much for taking the time to answer that one. Now, if you are interested in learning more specifically about these webinars, please feel free to reach out and talk to me about security level verification, to talk to me about the Excellentia Cyber tool, so the way to actually go through and do this analysis using the tool, or any sort of training. Please feel free to contact me at the information below. We also have a number of different social media that we can be followed on, so please, if you're interested in getting the latest on Exida, we've got Twitter, Facebook, and LinkedIn that we can all be found at. We have a number of upcoming training courses, so if you see anything in your area that you're interested in attending, or if you don't see things in your area, please go to exida.com/training for the full schedule. And always feel free to reach out to us if there is training you would like to see and aren't seeing it in your area. So with that kind of brings us to the close of the webinar. So if you have any questions, please feel free to place them in now, and I'll take just a couple minutes to answer them. And then if there are no questions, I just want to thank everybody very much for joining us today. I really appreciate having you as an audience and also all of the participation in the polls. So as of now, it does not look like we have any questions. So again, thank you for attending. And if you have any questions, please. Oh, it looks like we've got a couple. Okay. Let me see if I can pop this out to get it a little bit larger. Okay. So the question is, there appear to be a few examples of terminology that are exida expansions of the 62443, and so asking about really, what level of these are in line with the standard and how much of them is really exida developed, and that's a good question. So a couple of the terms that we'll look at that are exida specific are going with active and passive countermeasures. So this is something that we look at specifically when addressing the countermeasure effectiveness. And so kind of the standard requires that when you go through and do the analysis that you are using a well-defined method, that you are really kind of considering the approach and showing how you're going through and identifying the level of risk reduction that's being claimed. And so this is a method that's used to identify how effective that countermeasure might be and to provide a good understanding of whether or not it has the ability to stop the attack. The same thing with the cybersecurity kill chain. That is something that is looked at specifically for how do you justify attacks that are more complex. How can you say, well, this attack is going to be less likely to occur because these things are necessary? And the idea there is to make sure that we're not overly conservative with or overly optimistic and saying that this attack could never happen because it's targeted, but figuring out what specific areas need to be compromised can then help with that. As for the target attractiveness, so this is the target attractiveness, specifically the numbers that you apply to it are not from the 62443 standard, but target attractiveness is used in a variety of different methods for determining the likelihood of successful attack. But the examples presented are just to kind of show how different sizes of facilities can be used to determine the examples. So what I would say is that, so the terminology used, yes, some of it is exida specific, but it all fits with the overall approach and the idea of really determining security level verification in a reliable manner and in a consistent way that will address the requirements of the standards. So another question is then, if we're looking at security level 3 in terms of the risk reduction and thinking about the, what can we currently achieve in systems, specifically going back to our foundational requirements. So if we look about the requirements from 3-3, there are a number of different requirements. And so with our certification division, we have been working with equipment manufacturers as well as system designers. And so that is a good question because the number of certifications that we've done typically currently are falling more in the SL1, some in the SL2 range. But to say what is achievable in current systems, we have had some things such as data diodes that have been looked at for high levels of certification. And so understanding that even if not every component could be certified to a certain security level, if we look at our most critical zones, so areas where the BPCS or the safety system could be compromised, then providing the additional inclusion of certain firewalls, different ways to improve the segmentation, both physically with the limiting of access, we can make justifications of how these systems can be used to achieve the specific security level needs. So by addressing both the overall likelihood of the incident occurring as well as using what's currently available in the systematic capability, what's currently there in the industry, we can go through and show how different security levels can be achieved as needed. So thank you very much. Those are two really strong questions. I'll be happy to follow up more with them, but I think we are at the end of our time. So thank you very much for joining and listening to the webinar. I really appreciate having you all on as an audience. And so enjoy the rest of your days. Thank you.